Hey, 12th graders. So we are moving on from talking about just interpreting exponential models. So, like our first half of these notes was just interpreting and being able to understand what's going on within the exponential models. And now what we're doing is we're creating exponential models. And this is going to play off of some things that we're super familiar with, this idea of like a certain number of unknowns. We need to have that amount of information in order to be able to solve for those unknowns. There's also going to be a slight change. We're not going to be able to use, sorry, excuse me. We are not going to be able to use our simultaneous equation solvers because we are not creating linear equations. And we know that our simultaneous equation solver or our systems of linear equations option on our calculator is only for linear equations. So we're going to have to talk about how to handle that. So some things that are familiar and some things that are not. So a classic model that we're going to be creating with an exponential, this is supposed to be f of x, by the way, not f of c. F of x. A classic exponential model that we create is talking about like a cup of coffee or like something being left out in room temperature and watching as the temperature declines to meet the room temperature of this hot object. So we're developing an exponential model for my cup of coffee on my desk. We are measuring the temperature at regular intervals. The room temperature is 20 degrees Celsius. The table to the right shows all of this data. So the moment that we are given information in an applications problem, we should pause and ground ourselves in the problem, right? Take a look. 95 degrees Celsius, that's a really hot cup of coffee. Okay, it made a pretty big jump down to 79, 66, 56, 48, and it keeps going down, but just not making as big of jumps. And we know eventually it's going to kind of taper off and we think, okay, the coffee is never going to get colder than 20 degrees. So when it says to develop an exponential model, we've already kind of grounded ourselves in this idea that our asymptote, our horizontal asymptote, linear horizontal asymptote, is going to be at y equals 20. And so how did I know that? I know that because I've done these problems a million times. What you should know is that whenever we're thinking about this idea of a decreasing exponential model, there will be a horizontal asymptote, which will be the plus c, right? This will be y equals c, where it'll start to taper off at. And then we have to connect the idea of what this graph looks like, what we know this graph will look like, to what the context of the problem is. Well, it'll taper off and start getting really close to essentially equal to room temperature, but it'll never go below room temperature, right? You wouldn't pick up a piece of, or like a cup of coffee off of the table and it's like ice cold, like it's been in the refrigerator, right? Because it won't ever go below that room temperature. So we've already solved for C just by grounding ourselves in the problem. This is when I first solved this problem, I did a classic mistake where I didn't read the first part of the problem. I just looked at developing a model and I was like, cool, I've got E, which is a number. Remember, E is Euler's number. It's 2.71 something, something, something. So that's a number, but K is a variable we need to solve for. R is a variable we need to solve for, and C is a variable we need to solve for. X is our input, f of x is our output, E is just a number, our exponential number. And so we have three variables we need to solve for. And when I first looked at this problem, I was like, I have more than three pieces of information. I'm golden. I'm good to go to make a system of equations. I can solve for those variables. And then I realized as I started to solve, I was like, this is getting too complicated. And then I had to go back and reread the problem to pick that 20 out of there. So there's more than one way to get through this part of the process when you're problem solving, but just don't forget that there's numbers up here that are going to be really helpful. So don't overlook it. Something else that I've noticed that's really important here is at time 0, right? We have that initial value. That initial value is 95. So typically when we're talking about initial value, it's this number in front of our exponential piece. But now that we have the plus c, we remember we can look on the very front of our notes. K plus c is our initial value. Well, we know what c is. C is 20, and we know our initial value is 95. So we can actually solve for k also right now. K is 75. So fantastic. We've solved for C, we've solved for K, and now the only thing we have left to solve for is R, which, one unknown, we only need one piece of information to make one equation. So we are in a good spot. I'm going to go ahead and start grounding myself in what I have so far. So I have K, I don't have R, but I do have C. Okay, so I just need to solve for R. You can take any of these coordinates and plug them in and solve for R. This is the idea, the thought process is if you want to solve for a variable, you want to get rid of this and get rid of this, so there's only one variable left on the page. Once you have only one variable left on the page, then you can solve things. You can numerical solve it, right? So our goal is to get rid of as many variables as possible, and how we get rid of variables is by plugging values in for them. And since that x and y value go together, I go ahead and do that. You can numerical solve for this, and we get that R is approximately negative 0.23995, yada, yada, yada. So when it says to develop an exponential model, these are all the pieces that I need for an exponential model. I will finish up this process by writing my final exponential model. As long as you do 3 sig figs up here, that is fine. 3 sig figs would have been a little bit more complicated, so I just left it with more than 3 sig figs. We can tell that this is going to be a decay, not because the base is small, but because the exponent is negative. So remember that there's sometimes a variety of things that help us see whether it's going to be a decay or an increase. Growth is that opposite. Okay, use your model to find the temperature of the coffee after 8 minutes. So that's F of 8. We just go ahead and plug 8 in. It's really important for these guys to use the exact value. Oops, not 200, just 20. It's really important for these guys to plug in the exact value, not just type in the decimal. If you need to type in that decimal, then type in as many decimal places as you can, because this will actually have one small difference making a big change in your final answer. So definitely make sure that you use the exact values. Since I didn't ask you to calculate this, I'm assuming most of you didn't and just wrote it down. So I won't ask you to calculate for the rest of this guy because I don't think you have this in your calculator. So we'll just go through and finish this whole problem together. So this is approximately 30.999. It keeps going on like that, which means for 3 sig figs, that's 31.0 degrees Celsius.